Alright, welcome to a new lecture. In the previous lecture we learned about the physical basics of railroad and steel wheel interaction, and we got an overview about the most important elements of railway infrastructure. Now we will take a deep dive into the central link between the rails and the ballast, the railway sleepers. As we have learned, the rail faces the stress of the railroad wheel. These stresses are transmitted from the rail to the structure it is mounted on. This stress can be split into three components: vertical stress, horizontal stress, and a torque at the bottom of the rail. Stress is caused by the weight of the train and by dynamic forces such as braking or acceleration. The horizontal component is caused by guiding forces in curves or the hunting of the wheel sets. As the wheels do not run on the center of the rail but offset to the interior of the rail, the eccentricity of the force application point causes a torque at the bottom of the rail. To transfer these forces to the sleeper below the rails without moving them relatively from the sleepers, the rails are fixed on the sleepers with fastenings. Another stress that has to be considered is the contraction or expansion of the rails due to the temperature, which causes longitudinal stress on the ballast and the sleepers. Thus, railroad sleepers execute two basic functions. First, the load transfer. The sleepers distribute the stress from the relatively high surface pressure of the rail sleeper contact into a lower surface load in contact with the ballast. And second, the resistance to displacement. The sleeper or the support of the rail feet on the sleeper guarantee the track geometry and the gauge. After we now understand the basic functions of sleepers, let's have a look at the most important types that you will encounter in railway systems. Sleepers are distinguished by the material they are made from and by their overall design. As for latter, the distinction is commonly made between longitudinal and cross-sleeper tracks. In ballast bed, the cross-sleeper track is the most common on all railways, whereas longitudinal sleepers are infrequently used on slab track. Slab track is a type of track where the sleepers are resting in poured concrete instead of a ballast material, and this is giving them a particularly stable geometry and a long service life. Slab track will be an element of a following lecture where we'll look at this topic in deep. There are also many more variations of types, but this should give you at least an overview of the most relevant designs that you will encounter. As for materials, sleepers are commonly made from concrete, wood, steel, and artificial wood. The choice of material for the sleepers to be installed is made on the basis of technical, operational, and economic considerations. So let's focus on each one of them. Wood sleepers. On normal gauge railways, wood sleepers are usually made from hardwood like oak or beech. On lighter applications like trams or subways, softwood can also be used. As they are made from an organic material, these sleepers can and will be attacked by pests, and in consequence they lose their strength when exposed to moisture over time. To extend the service life, wooden sleepers are usually impregnated in tar or creosote, making them more resistant to pests, but also hazardous. Wooden sleepers can only be laid in ballasted bed and they are not suitable for slab track. They present a few advantages. Wood sleepers are lightweight. For example, they weigh between 80 and 120 kilograms, which makes them easy to be replaced and handled without the need of heavy machinery. Elasticity. Because wooden sleepers are elastic, they dampen vibration and reduce the wear on the ballast. Low height. Compared, for example, to concrete sleepers, wood sleepers give some additional centimeters of clearance, which can be useful in tunnels or on bridges. Unfortunately, wood sleepers present a few disadvantages, for example, weathering. Despite the impregnation, wood sleepers are susceptible to weathering and they tend to lose their stability over a few decades. Cracking tendency. Component failure can occur under very high loads. The incremental loosening of the fastenings under load, and the environmental impact due to the impregnation with toxins like creosote. Steel sleepers. Steel sleepers are subdivided into through sleepers and Y-shaped sleepers. Through sleepers were made from mild steel, but new through sleepers are not commonly manufactured anymore. Resupply is generated usually from refurbishment of old sleepers. Since the 1980s, there has been a new type of steel sleepers, the Y-shaped steel sleeper. It consists of two S-shaped bent, hot-rolled white flange main beams. As Y-shaped sleepers, disadvantages of the through sleepers are mitigated due to the continuous shape, which makes them highly resistant to displacement while reducing their footprint. For this reason, Y-shaped steel sleepers are being used in challenging situations such as steep climbs and very tight bends, while delivering a high stability and a high resistance to displacement. Usually, their main benefits are reduced costs of production in difficult locations, as their lower required footprint reduces the logistical needs at the construction site, for example by less excavation material needing to be displaced, and a substructure and ballast layer that can be lighter and tighter. Y-sleepers can be laid on ballasted bed and on slab track. They present a few advantages such as long service life up to 70 years. They are lightweight. Like wooden sleepers, steel sleepers are characterized by their low weight, between 80 and 120 kilograms, making them quite easy to be replaced and handled without heavy machinery, especially in difficult locations. They provide a low height because they have a very high resistance to displacement due to their concave shape. The steel sleeper lies firmly in the ballast and therefore has a higher resistance to displacement. Unfortunately, they also have a few disadvantages. For example, they have high manufacturing costs compared to concrete sleepers, and as through sleepers, they have a low stability of track geometry. Concrete monoblock sleepers. Today's most common sleepers are concrete monoblock sleepers. That is, sleepers that are made from one solid piece of pre-stressed concrete. Since the 1940s, with the ubiquitous use of concrete in wide applications, concrete monoblock sleepers replace timber sleepers in most usages. Due to their heavy weight of up to 300 kilos per sleeper, the concrete sleeper could only be introduced as a standard type of construction after the development of mechanical installation methods. The common sleepers laid in Europe on normal gauge lines weigh approximately 250 kilos and have a length of 2,40 meters. They provide many advantages, such as a long service life up to 50 years, cheap production costs, they are unaffected by weathering, and due to their heavy weight, they offer a high track stability. On the other hand, they also provide a few disadvantages. They are very heavyweight, which means they can only be handled with heavy machinery, and they are sensitive to damages. Pre-stressed concrete is sensitive to damaging, as for example a derailment. They are thus rarely used in tracks where light derailments can occur, like shunting yards or sidings. They are also sensitive to ballast quality. Because of their heavy weight and their low elasticity, concrete sleepers are particularly sensitive to the quality of the ballast and the subballast. Artificial wood sleepers. FFU, fiber reinforced foamed urethane synthetic wood for track construction, was developed in the 1970s in Japan. In terms of mechanical behavior and weight, the synthetic wood sleeper is very comparable to a timber sleeper. The bending stiffness is though higher of that of a classic beechwood sleeper. The bending tensile strength is even significantly high. This means that the synthetic wood sleeper can withstand higher elastic deformation without cracking. It has a high electrical resistance between the rail strands and shows no signs of embrittlement due to low temperatures. Artificial wood sleepers have been used for open steel structures and areas with low ballast height and switches. Their advantages are very long service life up to 50 years, they are recyclable, and they have a reduced environmental effect because of the lack of impregnation comparable to wood sleepers. They are dimensionally stable and they can be produced in any necessary shape. They are highly weather resistant and they have a high chemical resistance. Their main disadvantage, though, is that the manufacturing costs are about 4 times higher compared to a wood sleeper. Let's now get to the topic of rail fastenings. The rail fastenings have the task of supporting the rail against lateral tilting and at the same time providing resistance to the longitudinal forces in the rail. The longitudinal forces come from the driving and braking force and from thermal stress, as we learned. Fastener connect the rails with the sleepers to form a rigid track grid. This connection must be designed to be torsion and shear resistant. It must therefore not be possible to twist the rail at the fastening point in relation to the threshold or to move it lengthways. This gives the track grating a higher level of frame rigidity, and this is important for the positional stability of the track. Let's have a look at a typical fastening for concrete sleepers. There are large numbers of fastenings for concrete sleepers, which are also constantly being improved and further developed. The link between the rail and the sleeper is a construction in itself, which can take on very different forms depending on the design of the sleeper and the type of the rail. The rail inclination is achieved by a recess in the sleeper with the angle to be achieved, usually 1:40. A sleeper pad is installed between the rail base and the sleeper to increase friction and give some elasticity between the rail and the sleeper. The elastic material reduces vibrations and wear on the ballast. Angle guide plates hold the base of the rail and the rail pad in place. They prevent shearing and tilting and keep the track gauge of the rail. Screw and tension clips ensure the vertical stability while allowing for elasticity, thus reducing wear and the need of maintenance. This type of fastening is called a W-track superstructure, as it vaguely resembles a W. Another common type of fastening is used on flat sleepers without angled recess. A base plate with the desired rail angle is anchored onto the flat sleeper. Spring washers ensure a permanent tight fit. A sleeper pad is installed between the rail base and the base plate. The tension clips are bolted on the base plate with the use of T-shaped bolts to ensure vertical stability between the rail and the base plate. This type of fastening is called KS superstructure because its shape vaguely resembles a K. In practice, a multitude of different sleeper fastenings exist according to national industry standards and regulations. Okay, let's wrap up what we just learned. In this lecture, we learned that stress from the rails is transferred to the sleeper to distribute the load on the ballast on the superstructure, from which material sleeper ties are made and their different features, that fastenings connect the rail to the sleepers to form a rigid track grid, and that the rail inclination is realized either with angular mounting points on the sleeper or with angular fastening plates.